Over the last couple of videos, we've talked about the reactions of glycolysis and how those reactions can be used to generate energy. In this video, I'd like to unpack glycolysis as a model for how to think about metabolic regulation. So it's a cool topic. I am really actually looking forward to talking about it with you. So we've talked about previously how the accumulation of things like ADP and AMP activate glycolysis. So if you imagine you have a muscle and that muscle starts contracting, you start putting a load on that muscle, you're going to take ATP and start making ADP and inorganic phosphate out of it. We have buffering mechanisms modulated by the enzyme adenylate kinase, which is going to take ADP molecules. And as those start to accumulate by Le Chatelier's principle, we're going to drive this reaction to the right. We're going to start forming ATP and AMP. So as load goes up, you start to build up concentrations of AMP. And I said previously that one of the things that happens is AMP then activates glycolysis. And that formation of glycolysis is going to create more ATP, or that activation of glycolysis is going to form more ATP. It's a homeostatic mechanism that keeps ATP concentrations high even while you're under load. What I'd like to talk about today is how this regulation actually happens. So it turns out there's a couple of layers to this, but one of the main drivers of this is actually the enzyme PFK, phosphofructokinase, which I'll situate in the pathway in a second. But basically what happens with PFK is it is responsive to the concentrations of ADP, AMP, and ATP. So let's do ATP first. So ATP lowers activity. And we can see that because what we're measuring here is how much activity is occurring, so the percent of the maximum velocity of the activity, or the Vmax. And we're increasing our fructose 6-phosphate concentration, so we're adding substrate. And what we're seeing is as we add ATP, we actually move it over here to the right. It is less active. It takes more fructose 6-phosphate to get us up into an active form. ADP actually inhibits this relative to or activates this relative to ATP, right? So if we switch from ATP to ADP, we go in this direction, or maybe put it this way, for a given fructose 6-phosphate concentration, we're going to have a higher overall activity. And then finally, we'll talk in detail about this mechanism later, but it turns out fructose 2,6-bisphosphate is actually basically a direct readout of AMP concentrations, or it's related to AMP concentrations. It will drive it all the way forward. So both ADP and AMP, low energy molecules, uncharged forms of the ATP currency, activate this enzyme where ATP inhibits it. But this raises a question of, well, why this enzyme, right? We've got 10 enzymes in this pathway. We are inhibiting this one right here, phosphofructokinase. Why that enzyme and not some other enzyme in the pathway? Is there something special about it? And that's the question we're going to ask today. And as we ask that question, we're going to learn about some metabolic regulation principles in general. All right, so why this enzyme? Let's look at this step. And what I'd like to do is look at the energetics of this step. So what this step does is it takes fructose 6-phosphate, an ATP molecule, generates fructose 1,6-bisphosphate and an ADP. So it takes a phosphate and sticks it on to the 6th position of the fructose. The free energy, standard state free energy for this reaction is minus 20.2 kilojoules per mole. It's very favorable because you're hydrolyzing an ATP in the process. And what we can do is now think about this in terms of odds. I think this is actually a really good way to think about metabolism. So we can plug in this equation here. Basically, I've taken the classic equation of minus RT log of K with a delta G naught prime. I've rearranged it. And what we can think about this as is this is going to give us the odds, a probability if we freeze the reaction that the next reaction we see is a forward reaction, P plus, or the next reaction we see is a reverse reaction, P minus. If you plug in numbers for that, what you get is that it's 3,474 to 1 odds that you'll see if you just look in a cell that the next reaction you were to see would be this. Or another way to say it is for every 3,474 reactions you see going forward, you're going to see 1 going backwards. Okay? And I just realized I said in a cell, this is a standard state free energy, so this would only be in a cell that is at 1 molar everything, right? So this is saying all else being equal, there's 3,474 to 1 odds of going forward versus backwards. Okay. But this is actually happening in the context of a pathway, right? So if we put this here, this is, I've put a lone 3,704, I cannot say this word, 3,474 to 1 odds in the middle. That's step 3 of glycolysis. We can look up the standard state free energies for all of the other reactions and actually plug those into that equation, and we get this. So we get that some of the reactions, like this one here, are favorable, 846 to 1 going forward. Some of them are actually quite unfavorable. So the next step in this reaction, catalyzed by aldolase, is actually 4,700 to 1 odds against, so it would prefer to go backwards. And then some of the reactions are pretty much neutral. Like for example, 6 here, it could go forward, it could go backwards. They're very similar probabilities. But if you multiply all these numbers together, what you get is the probability of a molecule going all the way forward versus the probability of going all the way backwards. And it turns out that number is huge, right? This says 350 million to 1 odds of going forward. This is at standard state. So what this is saying is that if we set all species to 1 molar, that's what standard state means, right? So we set everything to 1 molar, and then we let it start relaxing, we let it start equilibrating, we're going to see a 350 million times more glucose going to pyruvate than pyruvate going to glucose. Okay? Hopefully that makes sense. What this says is the overall reaction of glycolysis is intrinsically favorable. And it kind of has to be, right? This is an energy generation pathway. This is the reaction that the rest of metabolism is getting coupled to drive it forward. So if this wasn't favorable, you couldn't do metabolism, right? So that's an interesting feature of energy generating pathways. Their overall delta G naught prime always has to be less than 0. It has to always be intrinsically favorable to do that because that's how we're making energy. Okay. Cool. But we said this was done at standard state, but molecules and cells aren't at standard state, right? They're actually at steady state. So there's this continuous flow of molecules through the cell, and they reach some steady state concentration of all the molecules. So I'm showing this, showing the values in a second. I'm going to show them again in a moment, but let's actually look at this picture. This is actually glycolysis drawn as tanks and dams. So we have a reservoir of water up here. We have an outlet down here. So this is, you could think about this, I've drawn pictures of rivers flowing. So this is, there's rivers flowing off the mountain up here. There's rivers flowing down to the ocean over here. This, in sort of technical terms, you would call this a source, and this would be a sink. It's a net flow downhill. But as it flows downhill, there are certain places that are higher than others, right? So this is a deeper place than this, where this is much more shallow. Now let's imagine I'm going to open up the dam here and let it flow. So I let water flow. And what we see is water accumulates in these upper reservoirs, barely appears here, right? Accumulates in these reservoirs, barely appears here, and then finally accumulates at the bottom. These are steady state concentrations. There are some concentrations that are very high. This is a very high concentration reaction. There are some concentrations that are very low. This is a very low concentration. And the high concentrations actually occur in front of reactions that are intrinsically unfavorable, or in this case, in front of hills, right? To get to steady state, you just have to fill up a lot in this tank. So in order to overcome, say, an unfavorable reaction, you have to build up a lot of reactants versus products. So we can actually see this in here. These are the steady state concentrations of a whole bunch of molecules in glycolysis. These were measured by this group and published here. This is one of the really nice early papers where they really sat and measured these things with very high rigor and reproducibility. These are in a mammalian cells growing in culture with oxygen. So this is our sort of cranking along, running aerobic respiration. If you know anything about metabolism, that means that glycolysis is on the way to aerobic respiration. And what you can see is this idea of certain molecules being depleted relative to others. So 1,3-bisphosphoglycerate, you might recall, in glycolysis, that's a very unfavorable intermediate. It's minus 1 kilojoules per mole of form, minus whatever it was, 18 to take it away. So it's barely populated. This is a log scale, so it's micromolar concentrations. Contrast that with pyruvate. Remember, forming pyruvate, that was extraordinarily energetically favorable, going from phosphoenol pyruvate. So it's multimolar. So, or millimolar, sorry. So it's, like 5 millimolar. So we have very wide distributions in the different concentrations of the different metabolites inside of glycolysis when the system is running at steady state. What that means is we have to adjust our free energies, right? So these are our standard state free energies. So if you make everything equal, what do these look like if we look at them as non-standard state energies, as cellular energies? So to do that, we plug in our concentrations of our molecules. So we know based on that paper, they've measured that the fructose 6-phosphate concentration, for example, is 1 millimolar, fructose 1,6-bisphosphate is 1.5 millimolar, et cetera. We've got an expression here that lets us describe this, right? So this is the energy, the current energy of the system. How far from equilibrium is it? What's the standard state bet? And then this is how far from that am I right now? What is our current difference between the standard state and our thing? Or another way to put it is, what is our equilibrium set point of the reaction? Sorry, no, that's what the delta G naught prime. That's our equilibrium set point. This is our current concentration of the system. Wow, I just said that totally weirdly. Hopefully you've seen this equation before. If not, you should go watch my video where I talk about it in a coherent way. Okay. Point here is we can plug in numbers for this. So we can plug in all the numbers. We know the delta G naught prime, we know R, we know our cells are at 310 Kelvin, we know the concentrations. Ultimately, what that says is this reaction is at minus 18.6 kilojoules per mole. So it went from minus 20 to minus 18.6. Not a big deal, right? Not a huge change. This means our probability of a forward versus reverse, I'm hiding under it, I'll go here, is 1,347 to 1. Okay. Now, we did this before for our standard state potentials. Remember what we saw? We saw a bunch of variation in these numbers. Now I'm going to do the exact math I just did, but for every step in glycolysis. And what do we see here? What do we observe? So maybe just think about that. Look at that for a moment. What patterns are you observing when you look at this? The pattern that I see is, man, all of those are basically 1-to-1. I mean, sure, 7-to-1 or whatever, but they're pretty close, right? There's not a huge bias one way or the other. And then we've got a couple up here that are still negative. They have a delta G less than 0. They're favorable going forward. The other thing we might do is we might multiply them together, and what we see is this is 500 million to 1 favoring, so it's still being very favorable to go forward. In case you think that, oh, that number's a little different than the standard state one, it's actually within the error on all of these numbers. There's a lot of rounding that's happening here. So it's basically the same amount of favorable to go forward when we're at standard state versus in the cell, but now we have a different distribution of these probabilities. So we can actually compare those head to head, right? So this is standard state. This is delta G. And yeah, what do we see here? This reaction, the fourth reaction, now doesn't care. It's 1-to-1. It was 1 in 5,000 to go forward, and now it just doesn't care. This reaction was 2,000 to 1 forward, and what is that? That is 1, 2, let's get the numbering right. It doesn't care. So what's going on? What happened? What this says is most of the steps in glycolysis have equilibrated. So I'm going to show this again in free energies instead of odds. Here are the standard state free energies of all of these molecules. So we have right here, negative reactions. This is actually the one we've been looking at. That's PFK. It's got a standard state free energy of minus 20.2, remember? This is aldolase. Remember, it had a positive delta G. It was a 4,000 or 5,000 to 1 against going forward. But now, if we say, what is the delta G, draw arrows to it, what we see is they've all equilibrated, right? They've all gone close to this 0 line. And in fact, I put in this gray arrow. This is actually the, let's see, get my numbers right, 1 to 7 and 7 to 1 line. Basically, this is within the measurement uncertainty of the experiments that that group did. So all of these are basically at equilibrium. These have a 1-to-1 odd of going forward backwards. So the only ones that are outside of that are over here. Those are the only reactions that are out of equilibrium. Another way to put this is actually just do a line. So now I'm doing a line showing the energies of these reactions in cells. And hopefully what you appreciate is most of these energies are about 0. And then we have these two weirdos that are very negative. Why are these two reactions out of equilibrium when the other ones aren't? Well, remember, I talked about this when I talked about concepts of metabolisms, if you've seen that video. But basically, I talked about how slow reactions cause a buildup of reactants. And I use the analogy of cars driving along. If we imagine we have a highway that has a city, and we ask how many cars are on the left and the right-hand side of that city. If there's plenty of room for all the cars, we would basically say, well, there's going to be the same number of cars. There's 6 on the left, and there's the same number of cars on the right. So the free energy for cars, right, the difference in the population on the left and the right of the city is the same. So we have a free energy of 0. If you add a reaction, or if you make it slower, you keep dumping in cars at the same rate, but now you have something that constricts the flow of cars through the city. You're going to build up extra reactants, and your delta G is going to be negative. So what this is saying is slow reactions cause the buildup of reactants, which means these two reactions that are out of equilibrium are slow. These other reactions are fast. You see this in biochemistry textbooks and content. We talk about slow reactions versus fast reaction. That's what we mean. A fast reaction is a reaction that has equilibrated or has time to equilibrate in the steady state of a cell. A slow reaction is one that just can't equilibrate. It's got a backup of stuff coming into it. And those two reactions, I've drawn it very small over here, so maybe it's hard to see, are right here, hexokinase and PFK. So think about for a second, why would that be helpful, having hexokinase and PFK be slow? Right? Evolution has had time to engineer this, to tune these up. Why would it make sense? So this is one of those that's probably not there by chance. What would be good about having these be slow? Well, first of all, so we'll come back to that answer. Let's actually talk about this with respect to glycolysis itself. So one of the things about hexokinase is, although it is slow and it's important, it's also not specific to glycolysis. So the reaction it's catalyzing is we're taking a glucose and a phosphate from that, and we're sticking it onto the 6th position, losing the glucose there. So we're making this G6P. And so glucose 6-phosphate can be used for glycolysis. In fact, this is the glycolysis step we've talked about. It goes on to do glucose 6-phosphate. This is now fructose 6-phosphate. But glucose 6-phosphate is actually the feeder for gluconeogenesis, which we'll talk about in a later video. Glycogen formation, which you've at least hinted at previously, and again, we'll talk about it later. And also the oxidative pentyl phosphate pathway. This one molecule has multiple different places it can go. So it's not really specific to glycolysis. Phosphofructokinase, by contrast, is specific to glycolysis. And so if we think about this as all pre-glycolysis here, all of this is pre-glycolysis here, we have this fructose 6-phosphate going forward. This is slow. Everything else is fast. We have a pattern of a slow step at the beginning. That's the rate-limiting step on glycolysis, and then all this downstream fast stuff. This illustrates a really important thing about metabolic control, is most metabolic pathways are controlled at a step that is early, slow, and favorable. And what this basically does is it turns these steps into a faucet. So it's early in the sense that, that the faucet is the start of the water flow. It's early. It's slow, and what that means is change here, change total flow, right? If I open the handle on this faucet a little bit, it'll get a little bit faster. If I close this handle a little bit, it'll get a little bit slower. Because this is the slow step in the flow of water, controlling the constriction point of the faucet controls how much water flows out of the faucet. And then finally, it's favorable. It means that it is downhill. We have a predictable direction. We see exactly the same thing happening here in glycolysis. It's our faucet, right? We have this slow step for the first step, this phosphofructokinase step. It's a slow step, so it's out of equilibrium. It's a favorable step, meaning if we make it go forward on that, it's going to go forward. And then if we control the rate of this step, we control how overall flow through the pathway. And so what we're seeing with PFK is that PFK, like many metabolic pathways, is early, and it's slow, and it's catalyzing a favorable reaction. Okay, so said a lot of things. Let's summarize them. The first is that AMP and ADP activate glycolysis and ATP inactivates. Hopefully this makes sense because this is basically saying if you need energy, turn on glycolysis. If you have enough energy, turn off glycolysis. One of the most important points of regulation in this is this phosphofructokinase, PFK. Most of the reactions of glycolysis are fast and thus near equilibrium. They basically have had time to have the products and reactants flow so that they're at equal on both sides. But PFK is slow and out of equilibrium, which means that controlling its rate controls the rate of the entire pathway. Okay, so hopefully that gives you a better picture now as you start looking at metabolism as a whole. You start looking at other pathways. You start saying, oh, look, there's an early regulatory step. That's where regulation is happening. That regulation is happening because it's early, it's slow, and it's favorable. Core metabolic motif, PFK illustrates it beautifully. Hope that was useful, and I will see you later.